In this lesson, we'll talk about profit, cost, and revenue. We've talked a little bit about marginal cost and marginal revenue, and we've looked at break-even points and all these different things related to costs and revenue, but now we want to look at the big one. We want to maximize our profits. Let's look at this image below. We've got a cost function and a revenue function given here, and we want to look at the profit. Remember, profit is revenue minus cost. And we can look at the profit by considering how far apart is the revenue curve and the cost curve. If we look around, we can sort of see that this maximum profit occurs somewhere right around here, where the cost and the revenue are as far apart as possible. Because this revenue is higher, we have a maximum profit at about 140 or so. What we'd really like to do, though, is figure out how we can find this point other than eyeballing it. So if we zoom in, we can take a look at how these two things fit together. 140 is where we said they were equal. Now, if you recall from a previous lesson, when the marginal revenue was bigger than the marginal cost, we said simply, produce another one. But the idea is if you produce another one, and the marginal revenue is still higher, produce another one. If the marginal revenue is still higher, produce another one. At some point, the marginal revenue will no longer be higher. On the flip side, if your marginal cost was too high, we said don't produce another one. But really, you might want to go backwards and produce a little less. And as you do that, there comes some sort of middle point, a point where the marginal cost and marginal revenue are the same, and this is actually what we're looking for. Let's mark down some of this. When marginal revenue is greater than marginal cost, we should keep producing, which is what we were looking at right here. When marginal cost is greater than marginal revenue, we should produce less, which is what's going on right here. And when marginal cost is equal to marginal revenue, this maximizes our profit. So this is what we're going to be looking for, just like right here. Notice that the revenue and the cost appear to be as far apart as possible when these two slopes are equal. Here's what our observation gives us. The maximum, or technically minimum, profit will always occur when the marginal cost and the marginal revenue are the same. When they're the same, we're at a place where a max or min could occur. Let's look at that a little bit more closely. We're trying to find a maximum profit. So the profit is revenue minus cost. Now what we've been doing this whole chapter is if we want to maximize something, we take the derivative. The derivative of the profit would be the marginal revenue minus the marginal cost, and we'll set that equal to 0. Again, setting it equal to 0 is where we tend to look for maximums and minimums. Now if I add the marginal cost to both sides, I get the marginal revenue is equal to the marginal cost. That's what we just said. But now let's think about this just a touch further. Remember, when I set the derivative equal to 0, that's what we called a critical point. That simply means that the derivative here being 0 could imply there's a maximum, could imply there's a minimum, or it might be nothing at all. But if we're looking for the maximum profit, it will occur at one of these places where the marginal cost and the marginal revenue are the same. It's a critical point, and the maximum will occur among the critical points. Let's take a look at this example. You've got the total revenue and the total cost curves, and we want to know where the marginal cost and marginal revenue are equal. Remember, when we look at where the marginal cost and marginal revenue are equal, this is like a critical point. We'll have to figure out which one gives us maximum profit. Often when I do this, I look at it from an angle. I kind of tilt my head so that I'm looking with this line being more horizontal. And I look and I say, well, about right here is one place where the slopes appear to be the same. And maybe somewhere about right here are where the slopes appear to be the same. Looking down, let's call this Q1, and we'll call this one Q2. At these points, we've got a critical point. Now let's just look at it. Right here, the revenue function is the line, and the cost is the curved section. The cost is higher than the revenue, so this is actually a minimum profit. Whereas on this side, the revenue is higher, so this must be the maximum profit. And you can also just look and see that the profit, say right here, is certainly smaller in the gap than it is right here, as well as if you go to the right side, the same thing occurs. Let's write down a little bit about these 2 points. At Q1, the cost is higher, giving a minimum profit. We definitely don't want that. That's actually a loss. However, let's talk about Q2. At Q2, the revenue is higher, giving a maximum profit. And so this is the point that we want. It could be that just because the revenue is higher doesn't necessarily mean it's a maximum profit, but in most practicality, that seems to be the case. Now let's draw the profit function. We're only going to need the right side of this graph, but remember, profits can be negative or positive. Let's mark down our points. Notice they are in a bit of a strange order, but I'm going to just call this one Q1, Q3, Q2, and Q4. These 4 points match up with a few things. Notice here that Q3 and Q4 are break-even points. They're the places where the revenue and cost are the same. But what happens is that at Q1, we have some sort of minimum profit, which is going to be negative. Let's draw it maybe down here. And then at Q3, we have 0 profit. At Q2, we get our maximum profit. And at Q4, we get our 0 profit again. And then afterwards, notice the cost is higher, so we would be going downward. Also, just to point out, at 0, the cost was higher as well. I'll write my profit somewhere down here. That gives us a picture that looks like this. You come down to the minimum, come up past the break-even point to the maximum, and then just go on back downward past the break-even point again. So what do we notice about this? Let's just make a few observations regarding profits and losses. The losses occur up to Q3, becoming worst at Q1. Notice this is where the profit function is below the axis. The profits occur from Q3 to Q4, maximizing at Q2. And you could mention that the losses start happening after Q4, but that part I'm not really going to worry about. Let's do a couple of examples with functions. We've got a revenue function and a cost function given to us, and we want to know the maximum profit and also mention the minimum profit. So the formula we want to work with is marginal revenue equals marginal cost. What that means is I should calculate these first. The marginal revenue is 5 minus 0.006Q. Notice all I did was took a derivative. And the marginal cost is 1.1. What we'll do now is set these two equal to each other to figure out where the maximum and the minimum could occur. If we do this, we end up with 5 minus 0.006Q is equal to 1.1. Now let's subtract 5 from both sides to get negative 0.006Q is equal to negative 3.9. And divide by negative 0.006 on both sides. This should give us our answer of Q equals 650. Now keep in mind this is a critical point. We don't know for sure that this is a maximum yet, and we're even given a closed interval. So we're really thinking about the last lesson where we were looking at global maximum and global minimum. Let's take these two endpoints, as well as this critical point, and figure out what the profit would be. To do that, I might write a profit function. The profit function is again revenue minus cost. So I have 5Q minus 0.003Q squared. And then minus the cost, notice the parentheses I'm using, of 300 plus 1.1Q. If I simplify that, I get negative 0.003Q squared plus 3.9Q minus 300. Keep in mind that I distributed my negative sign during that simplification. Alright, let's plug in 0, 650, and also the 1000 to figure out which one is the max and which one is the min. Again, we're plugging these into this profit function right here. When I plug these three values in, I get negative 300 at 0, 967.5 at 650, and 600 at 1000. Here's my maximum profit. We get a maximum profit of $967.50 at Q equals 650. And now the minimum profit is just the smallest. That happens at 0. We get a minimum profit of negative $300 at Q equals 0. As you might expect, if you don't produce anything, you're not going to make money. Let's look at one final example if the cost is a fixed value and revenue is the only thing that we need to consider. Some situations actually come up like this. A bus company is going to pay the same costs no matter how many people ride the buses. All they have to do if people are riding the buses is just run their bus schedule. They'll make money from the people buying tickets, and the more tickets they sell, the more money they make. They have to pay the same amount regardless. Same thing is true for, say, an airline company. If they don't sell all of their tickets, they still have the same costs. Let's take a look at this example. This whitewater rafting company is going to have the same costs no matter how many people actually take their rafts. And we've got a little bit of information about the demand here. For a price of $80, that's going to be a p-value. For the half-day trip, they attract 300 customers. For every $5 decrease, they attract 30 more customers. So if I decrease it by $5, I get 75, and the additional 30 customers will give me 330. From this, I can make a demand equation and a revenue equation and figure out how to maximize the revenue. Keep in mind that this is P and this is Q. So let's find the slope first. We get 330 minus 300 over 75 minus 80. That looks like 30 over negative 5 is negative 6. Now we can use our Q minus, you can pick, I'll use the 300 though. Q minus 300 is negative 6 times P minus 80. That gives us Q minus 300 is negative 6P plus 480. And then adding the 300, I get Q equals negative 6P plus 780. That is our demand function. So from there, let's make our revenue function. Remember, R is equal to PQ. So this gives me P times the Q of negative 6P plus 780. And then I'll get negative 6P squared plus 780P from this. Now I have a revenue function, and I can find the maximum revenue. You could use the negative B over 2A that we did in the past, but let's use this with our newer methods and say that the derivative of the revenue is negative 12P plus 780, and we'll set that equal to 0. We get negative 12P equals negative 780, and dividing by 12, I get P equals $65. If they charge this price, they'll maximize their revenue, and because their costs are fixed, this will also maximize their profit.